I am in my backyard using my telescope to look for galaxies. Galaxies come in a huge array of sizes, shapes, and colors. And believe it or not, a galaxy's color spectrum is one of the most important observations that astronomers can use to determine how far away that galaxy is from us. Now in this video, we're going to learn about the distances to galaxies. And we're not talking about miles here, we're not even talking about light years. We're talking about millions and billions of light years, the kinds of distances that you and I can barely wrap our heads around. How do we measure these incredible distances? How do we know how far away galaxies are? The best estimate of a galaxy's distance really comes from its color, and that's what we're going to learn about in this video. The story of how we determined the distances to galaxies spans 100 years of intense and focused research by some of the most brilliant minds in all of science. If you watched my video on using spectra to determine what elements are in a star, then this figure should look familiar. It's called an emission spectrum, and this is the emission spectrum for the element hydrogen. Each element produces a unique emission spectrum with different colored lines, and we can use the emission spectrum from a star or galaxy to determine which elements are in it. These lines toward the blue end of the emission spectrum have a shorter wavelength, while these lines toward the red end of the emission spectrum have a longer wavelength. The wavelengths are measured in a tiny unit of distance called a nanometer. This point on the spectrum corresponds with 400 nanometers, while this spot corresponds with 700 nanometers. In 1848, the French physicist Hippolyte Fizeau observed that some objects in space have emission spectrums that are shifted just slightly toward the red end of the spectrum, just by a few nanometers. So instead of seeing these lines for, let's say, hydrogen, he observed these lines. All the lines in the spectrum have shifted just a little bit toward the red end. This phenomenon that Fizeau observed later came to be called redshift. 64 years later, the American astronomer Vesto Slipher observed that nearly all galaxies have a redshift of a few nanometers. He even observed that the Andromeda galaxy, our nearest galactic neighbor, has a blue shift in which the emission lines are shifted slightly toward the blue end of the spectrum. Why would this be? Why would astronomers observe that objects in space have emission spectra that are slightly shifted toward the red end or slightly shifted toward the blue end? That leads us to the goal of this video. After watching this video, you should be able to use redshift to compare how far away different galaxies are from Earth, and calculate a galaxy's distance from Earth using redshift. To model what's going on with redshift in these galaxies, let's hop into the car where I'll show you a quick demonstration. Light travels through space in waves, and sound actually travels in waves as well. So sometimes we can use sound as an analogy or a model for the behavior of light in outer space. That's what I'm going to demonstrate for you right here. I have a Bluetooth speaker here. It is connected to my phone, and I'm going to turn on a tone. This tone is 1,000 hertz. That means it's 1,000 cycles per second. And I'm gonna drive past my camera, which is currently recording. I'm gonna drive past it as fast as I can go in the short length of the parking lot that I have available to me. And we're going to see how the waves produced by an object, such as sound or light, are affected by that object moving and the observer, my camera, sitting still. So I'm going to set my tone. All right, and away we go. All right, turn off my tone. Let's see what that sounds like. So let's look at what our sound waves did in the moving car demonstration. Remember that we're using sound as a model to try to figure out how light waves in space are affected when the object producing those waves is moving. I'm using a free program called Tony to analyze how the sound we heard in the car differed from the sound that we heard from the camera. What I've produced using Tony is called an acoustic spectrogram. And as we move from left to right on the spectrogram, we're moving forward through time. As we move from bottom to top on this diagram, the frequency of the sound that we're hearing is increasing. And any dark areas, these lines and splotches and things, are visualizations of sounds that we heard in that video. So let's analyze our spectrogram to see what we heard as I drove past the camera. You might notice this flat line right here. This line is the 1000 hertz baseline frequency that I was producing with the speaker in the car. At the beginning of the demonstration, the car wasn't moving yet. It was stationary. And the camera, our observer, is located right here. In this portion, I'm now driving the car with increasing velocity toward the observer. And then over here in this portion, I now pass the camera and I'm driving rapidly away from it. Do you notice this blue line right here? It tilts up as I approach the observer. And then it quickly dips down as soon as I pass the observer and start driving away. This shows that as I drove the car toward the camera while blaring that 1000 hertz tone, the camera, the observer, perceives this as an increasing pitch. In this demonstration, the tone rose from 1000 hertz all the way up to 1044 hertz. That's a noticeably higher frequency we heard. And over here, as I drive the car away from the observer, we see a rapid drop in the frequency. It goes from our baseline frequency of 1000 hertz all the way down to 968 hertz. And you can easily hear that rapid drop in pitch as the car passes by the camera. Now in this case, it's useful to have a basic understanding of the mechanics of waves and how frequency and wavelength are related, because we're going to be talking about both of them. A wave's frequency and wavelength are inversely proportional. As frequency increases, as the pitch sounds higher, the wavelength shrinks. The wavelength of these waves actually decreases. The opposite, but equally correct way to say this is that as the frequency of the tone drops, as it sounds like it's getting lower, the wavelength of those waves is getting longer. It's actually stretching out. Using sound as a model is really useful in understanding what the light from galaxies is doing as they move around. Now, the way that these waves are produced and propagated differ. Sound is a mechanical wave, light is an electromagnetic wave, but they share enough in common that this model really helps us to understand what galaxies are doing in space as they're moving toward us or away from us, as we'll see when we talk about the Doppler effect. What we observed in the moving car with the speaker is called the Doppler effect. You've probably heard of it. It's named after the physicist Christian Doppler. When we're talking about sound, the Doppler effect influences its pitch, but when we're talking about light, the Doppler effect influences its color. So the color of light is roughly analogous with the pitch of a tone. If a galaxy moves toward Earth, the light waves exhibit a shorter wavelength because the frequency of the light appears to increase. This corresponds to the light appearing more blue, producing a blue shift. The emission spectrum of a blue shifted galaxy might look like this. But if a galaxy is moving away from us, the wavelength of the light produced by that galaxy appears to increase, meaning that its frequency decreases. This corresponds with what we call a redshift. The light produced by that galaxy appears slightly more red. The emission spectrum of a redshifted galaxy might look like this. The farther the lines are shifted toward the red end, the more redshifted the galaxy is. So this actually answers one of our previous questions. Why do we observe different amounts of redshift or blue shift in different galaxies, as observed by Hippolyte Fizeau and Vesto Slipher? Well, this happens because if a galaxy is moving toward Earth, the wavelength of its light is decreased, making it appear more blue. But if it's moving away from Earth, its wavelength increases, making it appear more red. These changes in color shift the emission lines of the spectrum toward the red end if the galaxy is moving away, or toward the blue end if the galaxy is moving toward us. Do you remember how Vesto Slipher observed that nearly every galaxy that he looked at was redshifted? This means that most galaxies are moving away from us. Now, Slipher himself didn't really recognize the significance of this discovery, but a couple of other scientists did. One of them is Henrietta Swan Leavitt. Until sometime around the 1940s, we didn't really understand what galaxies were. We didn't know if they were nebulae, clouds of gas that were hanging around in our own galaxy, the Milky Way, or if they were their own little island universes, a bit more like how we currently think about them. Enter the American astronomer Henrietta Swan Leavitt. She used a special kind of star called a Cepheid variable to determine that what we now recognize as galaxies are incredibly distant. They're outside of our own galaxy. They're way, way far away. Now, you may have heard of Edwin Hubble by way of his association with the Hubble Space Telescope. Using Henrietta Swan Leavitt's calculations of the distances of these galaxies, Edwin Hubble identified an incredible relationship between a galaxy's distance and its amount of redshift. He found that the more distant the galaxy, the more redshift it shows. Today, we call this observation Hubble's law. Hubble's law sets up an easy and reliable way to measure a galaxy's distance from us by using its redshift. The greater the amount of redshift a galaxy exhibits, the farther away it is. So if you've been paying attention, you should have met the first goal of this video. You should be able to use redshift to compare how far away different galaxies are from Earth. Now let's tackle the next goal of this video. We want to be able to calculate a galaxy's distance from Earth using redshift. So let's talk about how to calculate a galaxy's distance from Earth, starting with a really important measurement called the galaxy's z-value. Suppose that we are observing a galaxy and it's moving away from Earth. There are two ways that we need to think about the light from galaxies. We need to think of it in terms of the light that's produced by the galaxy. We call this the emitted light. And we need to think of the light after it's traveled through space and reached us. We call this the observed light. We know that hydrogen produces a strong emission line at 486.1 nanometers, and we can find this emission line in any galaxy that we look at. Do you remember when I played the 1000 Hertz tone in the car as a baseline frequency to understand how the movement of the vehicle changed the pitch of the sound? Well, we can use this emission line at 46.1, or any emission line that we want to serve as a baseline to determine how that galaxy is moving. Let's say we measure this emission line in a galaxy, 46.1 nanometers, and let's call this galaxy Galaxy A. We know that the emitted light from this galaxy includes this emission line at 46.1 nanometers. But in the observed light, by the time that that light has traveled through space between that galaxy and Earth, we find that same emission line at 487.9 nanometers. The difference between these two values is positive 1.8 nanometers. The sign is important because it tells us what direction the galaxy is moving. In this case, the observed wavelength is larger than the emitted wavelength, so we give this difference a positive value. By taking this positive difference and dividing it by our baseline value of 46.1 nanometers, we get the value positive 0.0037. This is called the galaxy's z-value. Since the z-value for Galaxy A is positive, it means that the galaxy is moving away from us and so has a redshift. Between being emitted by that galaxy and traveling through space and reaching us, that light has been stretched out. Now suppose that we're observing a different galaxy. Let's call this galaxy Galaxy B. And in Galaxy B, we're observing the same emission line in hydrogen, 46.1 nanometers. But by the time that that emitted light has traveled through space and been observed by Earth, instead of seeing 46.1, we see a value of 485.8. This gives us a difference of negative 0.3 nanometers. If we divide 0.3 nanometers by our baseline frequency of 486.1 nanometers, we get the value of negative 0.0006. That's the z-value for Galaxy B. This negative z-value indicates that the wavelength of the observed light is a little shorter than when it was emitted. What that means is that the light has been compressed. This indicates that the galaxy is moving toward us because the wavelength has been shortened. Now that we know how to calculate a galaxy's z-value, let's get back to Edwin Hubble. Using Henrietta Swan Leavitt's distance data from many galaxies, Hubble was able to illustrate the relationship between a galaxy's redshift and its distance from us using a scatterplot diagram. For our purposes, I'm illustrating this diagram a bit differently than Hubble's version. Take a look at this diagram. What relationship do you see between a galaxy's z-value and its distance from us? As the z-value increases, what happens to the galaxy's distance? Can you quantify this relationship with any specific numbers or relationships? Pause the video and explain the relationship between a galaxy's z-value and its distance. It's easy to see that as the z-value increases, the galaxy's distance also increases. This is a direct relationship, and here's its trend line. If you line up the measured z-value with the trend line, you can move over and find the corresponding distance. You can also calculate the distance algebraically. If you take the time to calculate the slope of this line, you'll find that for every z-value interval of 0.001, the galaxy's distance changes by about 6 million light-years, with a y-intercept at around 14 million light-years. So you could just plug the z-value into this equation to get distance. Distance in millions of light-years equals z-value times 1000 times 6 plus 14. We need to multiply the z-value by 1000 in this case because the intervals for the z-value are in thousandths. Here's an example. Suppose you observe a galaxy with a z-value of 0.005. According to our graph, what's that galaxy's approximate distance? You can use the trend line to determine this, or you could try to calculate it algebraically with this equation. So go ahead and give that a shot. Based on the trend line, we can see that a galaxy with a z-value of 0.005 corresponds with a distance of around 45 million light-years. What if we find a galaxy with a z-value of 0.001? That corresponds with a distance of about 20 million light-years. Calculating a galaxy's distance using z-value is pretty much this easy. And although we're oversimplifying here a little bit, this really is how astronomers calculate the distance to a galaxy using its z-value. So when we look at nearly any galaxy, we observe that they are redshifted, and therefore they're moving away from us. What does this all mean about the behaviors of the universe? Pause the video one last time to ponder this question. If most galaxies are moving away from us, what does this mean about what the universe is doing? If nearly every galaxy we look at is moving away from us as measured by redshift, what that means is that the universe we inhabit is expanding. But we have to be careful about exactly what we mean by this. It's tempting to picture the galaxies in space all flying away from us, zooming away at these outrageous velocities. Picture a dozen or so cars driving away from a central point as fast as they can. But this picture is actually misleading. It's not that the galaxies are moving away from us. It's that the space itself in between them is stretching. So instead of a bunch of cars driving away from a central point, it's probably more accurate to picture the road itself as stretching. The cars aren't driving away and hitting the gas. They're just drifting away from each other because the road is stretching out or expanding around them. This appearance of galaxies all drifting away from each other in space is called Hubble flow. Galaxies that are farther away experience a greater stretching of space between us and them. And that's why more distant galaxies appear to be more redshifted. If you imagine rewinding the clock on the universe, this implies that at one time everyone was a lot closer together, all kind of jammed in the same place. This thought experiment of rewinding the clock and imagining what the universe might have been like at the very beginning is really the inspiration for the modern construction of what we call the Big Bang Theory. The idea that the universe had a specific moment in the past in which it began. This happened around 14 billion years ago. The Big Bang Theory is often largely credited to Edwin Hubble, but many astronomers and great thinkers contributed to the development of this idea, including the Catholic priest Georges Lemaitre. And there's mountains and mountains of observations that the Big Bang Theory explains really well. One of them is the CMB, or cosmic microwave background radiation. Another is the distribution of elements and mass in our universe. And of course, the Big Bang helps explain redshift, why we observe that some galaxies are far more redshifted than others, as we saw in this video. Let's review the goal of this video to make sure that you met it. After watching this video, you should be able to use redshift to compare how far away different galaxies are from Earth, and calculate a galaxy's distance from Earth using redshift. If you can't do that, go back and watch the parts of the video that you didn't understand. Until next time, remember, you can learn anything.